Hello and welcome. My name is Sonvi Singh and I am a chemistry faculty for IIT JEE Mains, Advanced and NEET. Today we are going to discuss about a very simple reaction known as Wurtz reaction. It is a very simple reaction but it involves some concepts which is not only from organic but they belong from physical as well as inorganic chemistry. So these are some beautiful concepts that we are going to discuss over here. So let's understand in this video. First we are going to discuss about what is the definition of Wurtz reaction. Now it proceeds via two mechanisms and scientists has proposed and scientists has given their scientific evidence to prove that the reaction is happening via these two mechanisms only. Okay, so we are going to discuss about all these three things, and after that we are going to discuss about some related questions from the Wurtz reaction. So I hope you like it. So let's understand what is the Wurtz reaction. So Wurtz reaction is reaction of when your substrate is Rx, which is present in sodium metal and dry ether, where dry ether is solvent and your product is RR plus NaX, where X can be fluorine, chlorine, bromine and iodine. And this whole Rx is known as alkyl halide. So reaction of alkyl halide in presence of sodium and dry ether is known as Wurtz reaction. So it's a very simple definition of Wurtz reaction. Now this Wurtz reaction proceeds via two mechanisms. First is free radical mechanism and second is ionic mechanism. So first we are going to discuss about free radical mechanism. As the name suggests, it involves some kind of free radical. Let's understand what is a free radical and how it involves in free radical mechanism. Okay. So in the very first step, as we all know, the sodium is a metal. And one of the definition of metal is that it gives electron, right? So Na plus gaseous state and one electron is your product in this case. Now in the second step, this single electron is going to attack into the anti-bond of Rx and which will generate R dot as well as X2 minus or X minus, because halide being more electronegative than carbon, then it will take away both the electrons of the bond via heterolytical cleavage. Okay, so this is your R dot, which is known as free radical, right? So this is your free radical which has 7 valence electrons. So free radicals has 7 valence electron. Now in the third and final step, this generated free radical will combine with another free radical that is generated in the reaction, and it requires 0 activation energy in gas phase. So your product is RR. That's right, free radicals are highly energetic. They are so energetic that they require 0 activation. They require nothing to proceed. Okay? Yeah. So I hope free radical mechanism is clear to all of you. Okay. Now the second mechanism that we are going to discuss over here is ionic mechanism. As the name suggests, ionic, so it involves some kind of ion. So we are going to look over here is what is ion and how it is going to affect the reaction mechanism. Okay. For this, for the first step, if we take two sodium atoms, then it will release 2 electrons and 2 Na plus gaseous state. In the second step, these 2 electrons are going to attack into the antibond of Rx, and halide being more electronegative, then it will take away both the electrons heterolytically and will form R minus plus X minus. So this R minus is known as anion in general, and carbanion when your R contains some carbon. So carbon containing negative charge is known as anion or carbanion, and anything which contains negative charge is known as anion. Okay. Now in the third and final step, this R minus is going to attack into the antibond of Rx and will eliminate the X minus and will form RR plus X minus. So this reaction mechanism is happening via SN2 mechanism. The third step is happening with the help of SN2 mechanism. What is SN2 mechanism? It's a bimolecular nucleophilic substitution reaction, right? So this is your ionic mechanism. I hope till now you understand about what is the definition of Wurtz reaction, the free radical mechanism, and the ionic mechanism. Now we are going to discuss about some beautiful concepts involved in this reaction mechanism, this reaction, Wurtz reaction. The first thing that we are going to look over here is why we are always attacking into the antibond of Rx. Okay. For this we have to take help of inorganic chemistry, and with the help of MOT, molecular orbital theory, we know about the bond order formula, which is nothing but half of Nb minus Na, where Nb is number of electron in bonding molecular orbital BMO and Na is number of electron in anti-bonding molecular orbital ABMO, right? So as you can see, when your number of electron in anti-bonding molecular orbitals are increasing, then your bond order is decreasing, and whenever your bond order decreases, your bond strength will decrease and finally your bond will break out. Okay, so this is the help of MOT. So any reaction that is going to proceed, it involves always the attack of incoming electron into the anti-bonding molecular orbital. ABMOs must be vacant to accommodate the incoming electron, and that will increase your Na and eventually will break your bond. Okay, so that's why we always attack into the anti-bond, and that must be vacant. Now now the second thing that we are going to discuss over here is representation of attacking electron. How? If two electrons are involved in a reaction, then the attack is represented as double edge arrow. So it is an arrow which has two edges, one edge and two edge, right? So this is your two edge arrow. So this is known as double edge arrow. And whenever single electron is going to attack, then it is represented as this. This is an arrow which has single edge, right? So this is known as single edge arrow, or sometimes we call it as a fish hook. Why do we call it as a fish hook? Because it look like this, right? So this fish hook is something like that. Okay, so it look like a fish hook, that's why we represent it as a fish hook. Okay, so this is it look like a fish hook, that's why we call it as a fish hook. Now the third and final thing that we are going to discuss over here is why free radicals are highly energetic, and they are so energetic than carbanion as well as carbocation. Carbocation. Okay, this is your reactivity order. So why this is happening? Why free radicals are highly energetic? They require zero activation energy. Why? Okay, for this we are going to discuss of MOT. As we all know, free radicals are what? It has 7 valence electron. Okay, so in any case, this is always involve a single electron, unpaired electron, right? It can't be paired. All the 7 electron can't be paired in the pair of 2. So it has always an unpaired electron. So free radicals are always paramagnetic in nature, and this paramagnetism increases your energy. So free radicals are highly energetic because it involves an unpaired electron, and which leads it to paramagnetism, and this paramagnetism is increase your energy. That's why free radicals are highly energetic. But in the case of carbanion and carbocation, in case of carbanion your valence electron is 8, so your all the 8 electron can be paired into the pair of 2, and which will generate 4 pair of 2 electrons. In case of carbocation, it has 6 valence electron, so all the 6 electron can be paired in the form of a 2 electron pair. So carbanion and carbocations are diamagnetic, so they have less energy. Less energy means less reactive, right? So I hope you understand about this. Now the final thing that we are going to discuss over here is what? Okay, now, okay, just a minute. Yeah, final thing and fourth thing that we are going to discuss is As we all know, free radical has 7 valence electron, which is less than 8 electrons. So it would like, free radical would like to accept an electron to complete its octet. So whenever somebody is going to accept an electron, it is known as electrophile. Can we say that free radical is electrophile always? No. Free radical can be nucleophile as well as electrophile. Let's see how. So in case of free radical are nucleophile or electrophile, it will depend on the substituent Z which is attached with free radical. So if a species Z which has lone pair like NH2, lone pair, OH, like something like that. So any species which has lone pair and directly attached with free radicals, then its energy profile look like this. This is your energy. Okay. So this free radical has one unpaired electron, and nitrogen or oxygen which are more electronegative than carbon, then their energy is less and they have lone pair. Okay. Now these are atomic orbitals. So with the help of MOT, we know the equally number of molecular orbitals will generate like it has 2 AOs, 1 and 2, then it will generate 2 MOs, molecular orbitals. It has, if somebody has 2 atomic orbitals, then MOT says that it will produce equally number of molecular orbitals. So it has 2 atomic orbitals, then it will produce 2 MOs. Okay. So first is bonding molecular orbital and the second is anti-bonding molecular orbital. So how many electrons are there? 3. Okay. And how we are going to fill them? According to Aufbau principle. 1, 2, and this is present in anti-bonding molecular orbital. So your bond order is half of number of electron in bonding molecular orbital 2 and number of electron in anti-bonding orbital is 1. So your bond order is 0.5. Okay. If we can give this electron, if we throw away this electron, then your number of electron in anti-bonding molecular orbital will be 0. So your bond order is 1. So as we can see, if we throw away this electron in anti-bonding molecular orbital, then your bond order is going to increase. And when your bond order is going to increase, the tendency of donating electron increases. So this free radical is going to act as a nucleophile because it is donating its electron to increase its bond order, which is favorable. Okay. So when your Z contains some lone pair, then the free radical act as a nucleophile. And when your free radical contains a species which does not have lone pairs, right? Like something like that. Then what happens? Let's see what happens when the substituent that is going to attach with free radical does not contain any free radical any lone pairs. So this is your energy, this is unpaired electron or free radical, and this is the vacant orbital of boron. Although boron is less electronegative, so its energy must be high, but free radicals are highly energetic. That's why its energy is up than the boron. So this is your atomic orbitals of free radicals, and this is your atomic orbitals of boron, right? So it will generate equal number of molecular orbitals. This is BMO and this is ABMO. So it has one electron. So what is your bond order? So half of 1 minus 0 is equals to 0.5. If it is going to accept one electron, now your bond order will be what? NB minus NA. Now NB is 1 and 2 minus 0, so your bond order is increasing. So whenever we are accepting an electron, then its bond order is going to increase, which is favorable for the reaction. So in this case, your free radical will act as a electrophile. Okay, so free radical is electrophile and nucleophile. It depends on the substituent that is attached with the free radical. Okay, so I hope these are some beautiful concepts that might interest you in the organic chemistry. So this is for today. I hope you like it and you enjoy it. So please share it and subscribe these things. Thank you all.